I want to talk about is some exponent rules. So everybody knows that a to the fifth means multiply a by itself how many times? 5. So that's a times a times a times a. 1, 2, 3, 4, 5. Okay, so you're not stupid. I know that you get that. Now, exponents are totally obvious for whole number powers. For zeros and negatives, they're a little bit weird. So we're going to find the pattern and explain a little bit why negative exponents and zero exponents behave the way that they do. So what's 2 to the third? 8. What's 2 squared? And 2 to the first is 2. Okay, so what's happening as you go from, what pattern happens as you decrease the exponent by 1? Your answer's divide by 2, right? So continuing the pattern, my exponent goes down by 1, right? So what should 2 to the 0 be? 1. Don't tell me it's 0 because it's not, okay? It's 1. And then continuing the pattern, what is 2 to the first? 1 over 2. What's 2 to the negative 2? 1 over 4. That's the same thing as 1 over 2 squared, right? I like kid movies, and I think about Lilo and Stitch, and I think about the part where she shakes the jar and says, "My friends have to be punished." Have you guys seen that movie? Okay, and so like I think about negative exponents, they have to be punished and sent in the basement. So it's goofy, but that's my, okay, so. And the same thing is true with, like, maybe 2s were special, we'll look at 3s. So what's 3 to the third? 27. What's 3 squared?
9.
And then 3. So what's happening as you go from here to here? Divided by 3. So 3 to the 0 is going to also be 1. So notice that the base doesn't matter. 3 to the 0 is 1. 10 to the 0 is 1, right? Anything to the 0 is 1. What will 3 to the negative first be? 1/3. And 3 to the negative 2 will be 1/9. So no matter how negative those numbers get, will my answers ever be 0? No, they'll also never be negative, right? Does that make sense? They're going to get super close to 0, but never all the way there. Close but no cigar. Close only counts in horseshoe and hand grenades. It's a really bad joke, sorry. Okay, so I said that anything to the 0 is 1, and this first question I made a little bit tricky on purpose. Is this negative sign part of what is to the 0? No, it's not, okay? So it's kind of like PEMDAS, which I can't say order of operations without stuttering, so I always say PEMDAS. So this is the same thing as -1 times all that junk to the 0, right? And PEMDAS says you do exponents before you multiply, right? So the exponent of 0 happens first and makes all that stuff into 1, and then you make it negative. So that's -1. If the negative were inside the parentheses, it'd be part of what was raised to the 0, and then it would be 1. Okay? All right, 5 to the negative third. Well, the first thing I'd think is that's the same thing as 1 over 5 cubed, right? And then 5 times 5 is 25, right? 125. 25s are great because you can think about money. Like 5 quarters is $1.25, right? So I kind of suck at arithmetic, so yeah. I don't know where my eraser button is. This is really frustrating. It occasionally comes and goes, or I just suck at technology. One of the two. Probably the second one. All right. How about this one? 1 over x cubed, yep. And that will actually happen a lot in calculus. You've got to translate between the 1 over x cubed and go back to x to the negative 3. It happens all the time. I don't know, somehow I didn't know that when I took calculus and it really hurt me. This one's a bit tricky and I'll explain it the long way and then you'll be able to observe the shortcut and use the shortcut. So x to the negative 3 is 1 over x cubed, right? And then y to the negative 5 is 1 over y to the 5, right? They each make their own fraction. Kind of like that division problem we had, right? So same process, how would you get the 1 over y to the 5 out of the bottom? Multiply by y to the 5 over 1 there, and y to the 5 over 1 there. And so the denominator cancels out, and you get y to the 5th over x to the 3rd. So the middle step is y, but there's a really, really easy pattern, right? What is the easy pattern? You flip them. The negative was sent to the denominator, right? The negative in the numerator was sent to the denominator. The negative in the denominator was sent to the numerator, right? And you can use that pattern without showing the work, but the work is why it's true and it's good to understand, right? So, okay. And then there are a whole bunch of rules for exponents, and I think that the best way to know them or memorize them is to think about something that you can just, you know for certain is true. So x squared times x to the 5th. That's 2x's multiplied by 5x's, right? So that's going to be logically x to the 7th. So what happened to your exponents? They added. So, and then there's only one base, right? So a to the n times a to the m is a to the n plus m, right? That's the rule. And the kicker is that these rules work for fractions. They work for like irrational numbers. So like if you have like x to the 1/2 times x to the 2.5, you can actually still add the exponents. So x squared to the 5th. I should have picked smaller numbers, but that's x squared, how many times? 5 of them, which then makes someone step ahead of me, makes x to the 10, right? So what happened to the powers? They multiplied. So that's a to the n times m. 2x to the 3rd, because the 2 is in parentheses, you have 2x 3 times, right? So 2x times 2x times 2x. So you're like, I know this, 2x times 2x times 2x. And that makes, so the 2 times 2 times 2 makes 8, yep, 8x cubed. Do you see that the power kind of distributed there? So so exponents distribute over multiplication. And I say that kind of carefully because they don't distribute over addition. So we'll discuss more what that means later specifically, but if you have, they do distribute in this case. So the first one here is a to the n, b to the n. That's the rule. Both things get raised to the power. And if the rule applies to multiplication, do you think it applies to division too? Yeah, because they're effectively the same thing. You also can think this is 2x times 2 over x times 2 over x, right? I'm multiplying straight across. The 2 is cubed, which makes 8. The x is cubed. So you have 8 over x cubed. So like in this next rule, you'll have both a to the power of m and b to the power of m. And then the last two rules, just wanted to discuss what happens when the power is bigger in the numerator versus when it's bigger in the denominator. So think about cancellation. If you have x to the 7th over x squared, how many x's can you cancel? 2, which makes x to the 5th. So what happened to the exponents? They subtracted. So the rule probably is m minus n. So what about x squared over x to the 7th? If you like canceled stuff there, what would that be? My first thought would be it'd be 1 over x to the 5th. Does that make sense? And that's the same thing as x to the negative 5, right? And so the thing is that subtraction rule also works in the case that the numerator's power is less than the denominator's power. It still works. Just that you should always give your answers with positive exponents only. The ALEC system will tell you that you're not quite right if you don't put it back into a fraction with positive power. Okay, so there's all the rules, and they can be applied in complicated manners. They are definitely important for you to know. It's probably the case that your first quiz will just like have this list and make you fill in all the rules, in addition to apply them. All right, so this one. So 5x to the negative 3, 3x to the 4th. So multiplication is both associative and commutative, which means I can change the grouping and I can change the order. Does that make sense? So I can change this into 5 times 3, x to the negative 3, x to the 4th. Most of you do that in your head because you know that it works, and that's totally fine, okay? I'm just showing you all the steps in class so that you understand why it's this way. And what's 5 times 3? 15. And then with these x's, what happens to the powers? They add. And what's negative 3 plus 4? 1. So 15x. You don't need to write 1 because 1 is the default power, right? Okay. Part B, you can do lots of ways, and I try to sort of think about what is the way that you would see first. What is the thing that you think you should do with part B first? Like, there's lots of ways to do it right, so what's your first instinct?
Reduce 9 over 6.
Reduce 9 over 6. Okay, so let's do that first. That makes 3 over 2. Now, would you prefer to subtract, or would you prefer to move the y's? Let's move the y's. Okay, so the y to the 4th goes up, the y to the negative 7 goes down. Does that make sense? Or, I said that wrong. Y to the negative 7 goes up, right? No, crap. I almost swore on camera. So y to the negative 7 goes down. Y to the negative 4 goes up. Okay. Whoosh, dodge that one. Y to the 4th over y to the 7th. Okay. Whew. And now you can use your subtraction rules, or you can just think, oh my goodness, cancelization. So you've got 4 y's over 7 y's. How many y's cancel? 4 cancel, and there are how many left? 3, and where are they? On the bottom. Perfect. So 3 over 2y to the 3rd. Subtraction also works. So here's another way. You could have said 3 over 2 y to the negative 7 minus negative 4. But the part that always gets students is this double negative. They almost always would mess this up and sort of miss that. Does that make sense? And so also let's just double check if that's actually the same thing. You get 3. So minusing negative 4 makes adding 4, right? So negative 7 plus 4 is negative 3. And then this just moves down and joins the 2 in the denominator. So same thing, right? The subtraction rule works, but I think that probably it's easiest to get rid of the negatives by moving the stuff first. That's just my suspicion. Okay. All right, in part C, the 2 is not to the 4th power, correct? Okay. The second 2 is, right? So can you compute negative 2 to the 4th?
16.
16 is right. Is it negative?
No.
It's not negative. Does that make sense? Why? Because you've got 4 negative 2's. So those 2 make positive 4. Those 2 make positive 4. So overall it's positive 16, right? So that's 2x to the 4th. And the thing that always trips students up right there is that this negative sign in the middle doesn't go away. Because of PEMDAS, first you exponentiate, and exponentiating takes off the negative on the 2, right? That becomes positive 16x to the 4th. And so if I have 2x to the 4th, or you have 2x to the 4th, and you owe me 16, I take your 2, and then you still owe me, right? How many do you owe me? 14. Negative 14, yep. If anybody has trouble with adding and subtracting negatives, I think that the best analogy is temperature. So if you think it's 2 degrees above 0 and then goes down 16 degrees, it's now negative 14. That's my favorite analogy to figure out like how to do them in your head. All right, this part D, I have 3x to the 4th, y to the negative 3rd, all to the negative 2. So the first thing is that power has to distribute. So first it goes to the 3. So you've got 3 to the negative 2. When it goes to the x, do the powers multiply or do they add? Multiply. So it's x to the negative, how much? 8. Okay, and then y to the 6th. And in your final answer, you've got to put all of the negative exponents back into the denominator if they're in the numerator, or into the numerator if they're in the denominator. So if you make your fraction bar, who stays on top? Who goes down to the bottom? And it becomes 3 to the positive 2 then, right? And who else goes down? Yep. And are you quite done?
You just gotta square it.
Mm-hmm. So y to the 6th over 9x to the 8th. If you knew you had, like, if you're able to, like, you know, you can square that 3 right away also if you wanted to. You don't have to, like, make 2 steps. But, okay. So, we had whole number powers. Now, it turns out that there are also, that rational powers are the same thing as roots. As in, have you guys heard that a square root is the same thing as a power of 1/2 before? Yeah, so that's kind of what we're talking about here. The nth roots, we use radicals or rational exponents, and I said it happens. So the square root of b can be written as either square root b or b to the power of 1/2. And in this case, both expressions denote the positive square root when there are 2 real square roots. And that's a bit technical, but what I'm trying to say there is that when you find, say, square root 9, the question you ask yourself is what number squared gives me 9? And technically there are 2 answers to that question, right? Technically the answers are 3 and -3, both numbers squared and 9, right? But you want this square root thing to be a function, so the input of 9 only goes to one output. And you say, okay, well, I'm just going to say that's +3. Kind of give it the most common one. So that's what they mean by 2, and your book calls it the principal root. So a lot of this homework today, like if you do actually do it, is super easy. 8 to the 1/3 is the same thing as the, what kind of root? Cube root of 8. And so you ask yourself, what number to the 3rd power gives me 8? 2. I won't always, but I did put in this clause for a reason. Square root of -4. So does any number squared make -4?
2. You said any number, not any real number.
Oh, I did say any number. Okay, so technically, 2i is the answer, okay? But it really is not possible.
With any real numbers.
Yeah, so we're going to assume real numbers unless otherwise specified. We'll discuss I specifically later on in this class, but not right now. And the point is that there is no number squared makes -4. If you square positives, you get a positive, right? If you square negatives, you get a negative, because the negative is also squared. So that is not possible. Okay, the 4th root of 10,000. I know 10,000 is huge, but what would be your best guess?
10.
10.
And -10.
Nope. Only gives the positive answer. Because this is a function, the principal square root is always the positive one only. If it wants both of them, it'll put this ± symbol in front of it. Have you guys seen that symbol before? Yeah, okay. Okay, so this next one is the 5th root of -1. And you saw that we couldn't square root a negative, but does some number to the 5th power make -1?
Yeah.
-1, yep. Okay, and 0 to the 1/8. The 1/8 is weird, but, you know, 8th root of 0. So what number to the 8th power gives us 0? 0. So generalization, if the kind of root you have is an even root, like a square root, a 4th root, you can't root negatives. Does that make sense? If it is an odd root, like a 3rd root, a 5th root, a 7th root, then you can root the negatives. Does that make sense? Okay. All right. Now, the other rule that we're going to use has to do with when you have a power that is not 1 over a number, that it's like 5 over a number or 10 over a number. So there's like both a number other than 1 in the numerator and a number other than 1 in the denominator. And the general rule of thumb is that if you have b to the n over m, I guess they did it backwards. Well, anyhow, the number in your numerator is the regular whole number power. The number in the denominator is the root. So that's the same thing as the mth root of b to the n, or it's the same thing as the mth root of b to the n power. It doesn't matter what order you do it in. You can either choose to power first and then root, or root first and then power. There is one way that's better and easier, and that will be totally obvious in example A and B of example 4. So I think this will make more sense with numbers. So let's do example A and example B, and let's see if they make sense. So with -8 to the 5/3, you have two options. You can either do -8 to the 5th, and then you can third root it, or you can do the third root of -8 and then 5th power. They're going to give you the same solution, but one of them is a hell of a lot harder without a calculator. Does anybody want a 5th power at -8? Not particularly, right? And then you'd have to third root it, which would be even worse, right? So, but can you do the second one? What is the third root of -8? -2. And then you have -2 to the 5th. So that's 4, -8, positive 16.
-64.
One too far. Negative 32. Okay. And this one, the next one, I know it's not totally obvious, but that 4 is a power. It's not like 324. So you probably don't want to do 32 to the 4th power, do you? No. But you can translate this into the 5th root of 32 and then take it to the 4th power. Is that doable? Yeah. So we know 2 to the 5th is 32, so what's the 5th root of 32? 2. Okay, so you've got 2 to the 4th, and that is 16. Okay, great. All right, so this next one, there aren't any numbers. Well, I mean, there's 5 and a 2. But so we're going to apply those exponent rules, but we're just going to do them with fractions. So the first thing I want you to do is rearrange the 5 and the 2. So make it into 5 times 2. Or you could, can we just say 10? Because, like, I want to skip steps too. And then this next thing, the first y, what would that power on the y be as a fraction? The first y. The second y is 1/3. The first y is y, the 4th root of y cubed. So 3/4, beautiful. Yeah, the whole number is the numerator, the root is the denominator. Does that make sense? Okay, now the cube root of y, that's y to the 1/3, yep. All right, now, you got to think about those rules with exponents we just learned kind of abstractly. You have y to a power times y to a power. What happens to the exponents? They add. And because they're fractions and they're adding, you have to get a common denominator within your exponent. Oh my God. Can you take it? Okay, we'll hope you can take it. So what is the common denominator going to be? 12. So 3/4, making that into 12 is 9/12, right? Mm-hmm. Making 1/3 into 12ths is 4/12, right? Mm-hmm. So that's 10y to the how many 12ths? 13/12. Now, I'm not 100% certain which form Alex would like you to give that in. So with me, that's totally fine. 13/12 is acceptable. But just in case, it's the same thing as the 12th root of y to the 13th, right? It's good to know both forms in case you know, you have to translate between one or the other. Okay, I'm going to do example D, and then we'll finish the rest of this one tomorrow. So we had to go over the syllabus, so, you know, wasn't quite able to do it all. So with this last one, the first thing that I would think about is that that power of 1/3 that's on the outside of the parentheses is going to distribute. Does that make sense? So can you do 8 to the 1/3?
Yes.
Yes, and it's 2. What happens to the exponents there?
They multiply.
They multiply. So what is 1/2 times 1/3? 1/6. Sorry for my bad fraction. Okay, and then what will 1/3 times 2/3 be? 2/9. So the same rules that apply for whole number exponents also apply for fractional exponents. And now what happens to those fractional powers since we have division? They subtract. So you have 2x to the 1/6 minus 2/9. What is the best common denominator there, or the smallest or lowest one? 18. Great. So that's 2x to the, what, 3/18 minus 4/18, right? So 2x to the negative 1/18, or 2 over x to the 1/18, or 2 over the 18th root of x. And I only give you that last one just because I want to make sure that if you have to give it that way in Alex, like on your initial assessment, you'll be okay. So let's see, there are radicals. So has anybody seen simplifying radicals before? Yeah, it's kind of like reducing square roots in some sense. So numbers are not so bad. I think everybody's seen the number side of it. So 18 is the same thing as 9 times 2. So you think about, like, how do I write this number as a product of two things where one of them has a nice square root, right? Okay, now how about variables? What happens to variables when you square root them? Do you know?
Well, it depends on the variable.
Depends on the variable and the kind of root, actually. So just as there's an aside, what's the square root of x squared? X. So what's the square root of x squared times x squared times x squared? It's kind of on the bottom, maybe you can't see it. X, yeah, it's x times x times x, or x to the third. So look at the square root of x to the 6th is x to the third. What happened to the exponent? It halved. So you can square root exponents that are even. So can you square root x to the 10th? Yep. Y to the 7th isn't an even power, so you can't square root that, but you could if you broke it into y to the 6th times y. Does that make sense? Yeah. Okay. And then there are parts, the 9 roots, the x to the 10th roots, and the y to the 6th roots, and they go outside of the square root. So that'll be 3 x to the how much? Is it Tani?
Yes.
Okay. No, it's okay.
The book
So
is
one
in-
of each.
Yeah,
Huh?
I went over there to go check and they said the book might not come until Monday.
Okay, 3x to the 5th, y to the 3rd, and then square root of 2y. Awesome. So Tani, I told everybody else that I'm going to scan the first homework assignments and put them on Blackboard. So that you can see, or the first practice problems, you can see them if you have a book. Okay. So, Okay, so that's square roots. Now, this next one's a 9th root. Wowza. Okay, this one is actually easier. So is everyone okay with part A? Yeah? Okay, with part B, remember that a 9th root is a power of 1/9? It's actually easier to think about that one, this second one, that way. So 8 So 8 is 2 to the third, right? Okay, x to the 6th, y to the third, to the 1/9. And the thing that's happening in the second one is that these exponents can kind of reduce. Like if technically speaking, if you have as the 4th root of x squared, that's the same thing as x squared to the 1/4, right? Does that make sense? Which is the same thing as x to the 2/4, right? So what does that simplify to? What is x to the 1/2? Which is the same thing as root x. Does that make sense? So it's kind of the case that when you're looking at something like this is a fraction. That's the numerator power. That's the denominator power, right? And you see how with this one, if I have like 6/9, that fraction reduces, right? And if I have 3/9, the fraction reduces as well, right? So the reason I had to write 8 as 2 to the third is that 3/9 will also reduce some. The 2 is the tricky part. Everything else is kind of obvious. Does that make sense? Okay. So this is the same thing as 2 to the 3/9, x to the 6/9, y to the 3/9. And the ones you'll see in calculus are probably going to be a little bit simpler than this actually, but it's good to still have sort of dissected how they work. Okay, so what does the power, and that's just the power that distributes, right? Okay. Now does anything reduce there?
All of them do.
All of them do, yeah. So 3/9 reduces to 1/3, so 2 to the 1/3. 6/9 reduces to 2/3. And 3/9 reduces to 1/3. Now it's a little bit hard to say what kind of form exactly the ALEX or the textbook will have their answer in, so it's going to be able to convert between lots of them. Does it make sense that all of these are powers of 1/3? So so I could make this into a big old cube root, and then what would be inside the cube root? 2x squared y, awesome. 2x squared y. And remember that the whole number of powers come from the numerators of those fractions, right? That's why it's 2 to the first, x to the second, y to the 1. And because they all are a power of 1/3, they can go inside of one cube root. If I had one that was a power of 1/3 and one that was a power of 1/6, you'd have to mess with it a little bit to make that happen. Okay? So that's pretty tricky. You're more often going to see stuff like this. That's far more common, okay? Probably also the one I'll test. Have you ever seen rationalizing denominators? Yeah. So the most common ones that you see are when you have a square root denominator, right? And how you rationalize that denominator is the whole idea of rationalization is that you don't want to have radicals in the denominator. It's okay sometimes, but the point is that want to be sure you can translate back and forth between these things. So the way to get the radical out of the denominator there is to multiply by root 2x. And you can't just multiply the denominator by something because then it's not fair and the numerator has not gotten anything. So you multiply the numerator by root 2x as well. And also think, why did I pick root 2x to multiply by? Yeah, when you multiply them together, the roots go away and they're gone, right? So I have 6 times root of 2x over just 2x. And then will that 2 cancel with the 2 in the root or cancel with something in the 6?
No, cancel with 6.
Cancel the 6. And what does that make? What's your final answer then?
3x root 2x over x.
3 root 2x over x. And I think if you put in the upper answer, into ALEX when you're working on your pi, it's going to tell you that you have to simplify it more. Okay, just you have to reduce the fraction sum. So square roots are easy, they're the most common thing. Stuff like 4th roots are a little bit more tricky. So this worked because when you multiply these two things, you get 2x squared. Does that make sense? In this next one, you have to get something that's sort of 4th rootable. So the first thing that I would say when you see a question like part B is look at the number and see, can I simplify that number at all, like the number inside the root? So can you work out the fourth root of 16? Yeah, it's 2. So let's make that into 30 over 2, which you could just say was 15 right off the bat if you want to. Fourth root of x. And now I'm going to tell you what to multiply by, and you're going to tell me if it makes sense why this is what you've got to multiply by. You multiply by the fourth root of x cubed. Because you need to make that into something that has a nice fourth root, right? Which means you've got to make it have a power of 4. Does that make sense? Do you get it? So like if that had been a cube root, what would I have multiplied by? So if that was a cube root and I had an x, I've multiplied by x to the second. Does that make sense? If it was a fifth root, I have to multiply by the fifth root of x to the fourth, right? You've got to make those exponents add up to this number. In this one, it's easy because you make those exponents add up to 2, right? And so I think that's something that gets glossed over a little bit in like in Algebra 2 classes, and actually honestly even the one that I taught, because like my students were just like, oh my god, this is so different, right? So it's the same thing, it's just that this one happens to be multiplied by the exact same thing, right? Whereas this one you have to manipulate it a little bit. And so the reason that works, we'll just show you in detail. So you got 15, fourth root of x cubed, and this becomes the fourth root of x to the fourth. That's why it works. So that becomes 15 fourth root x cubed over x. So I'm not going to do this in super detail, but what if I gave you 2 over cube root of x squared? Just tell me what you'd multiply by. Almost. Cube root of x. I think that's what you meant, though. Does that make sense? Okay, what if I gave you something kind of really weird? 10 over 2 seventh root of x to the fourth. Ignore the 2 doesn't really matter, does it? No. What matters is the radical. So here you had to make this into x to the third, so it would cube root, right? You've got to make this into x to the how much? 7. So we have 4 x's thus far. How many more do we need? 3. So 7th root of x cubed over 7th root of x cubed, right? Okay, so that's how the funky roots that are not square roots work, okay? That's how that rationalization works. The rationalization you're going to see in calculus far more often is this kind of thing. That happens a lot. We'll just do a lot with trig. And you're going to see, well, this one's a little different too, but this was not hard. Okay, so simplify this radical. That square root sign is humongous and over everything for a reason. It means it roots the numerator and denominator, right? So this is the same thing as square root of numerator. I'm going to pause on that for a second, and square root of denominator. And can you break up, I stopped with the x cubed because you can actually simplify it. How do you break it down?
Break it down to x squared and x.
Break it down to x squared and x. Okay. And the x squared is the only thing that can exit the square root, right? Okay, and it becomes x. So x root 5x over root y. And now this is a pretty easy one. You just want to get the root y out of the denominator. So what do you multiply by? Square root of y over square root of y. Exactly. So that's x. And then the 5x and the y can go underneath one square root sign over y. So that one's simplified. The most common kind of rationalization that you see in calculus is something like this. you don't actually usually do it with numbers, you do it with variables, but it's the same principle. So for this one, don't write this down because it's going to be wrong. Does it make sense why multiplying by root 3 over root 3 isn't going to do it? Because that root 3 would distribute and you'd have root 3 minus 3, right? So that won't get rid of the roots in the denominators. So let's X-nay that idea, and for some reason my eraser is dumb. I discovered it matters what buttons I choose first, so we're just going to scribble that out. Bad form, I'm so sorry. All right, to rationalize this denominator, use some special thing called the conjugate. So the conjugate is the sort of the expression that you're given in that denominator, except for the sign between the numbers changes. So 1 minus root 3, the conjugate of that is 1 plus root 3. And your teacher is going to use that word, so it's probably important that you know what it means. So has anybody seen that before? Yes? Okay. So in the numerator, the 6 distributes, and you get 6 plus 6 root 3. That's your numerator. Those parentheses aren't necessary, I just all of a sudden can't erase stuff. With these denominators, to multiply them together, first you do the 1 times 1, right? Then you do 1 times root 3, right? And then do, how I think about that is you take this first thing, distribute it to both things. Take the second thing, distribute it to this double distribution. And that method generalizes if you have like 3 things here, right? First thing distributes, second thing distributes, third thing distributes. So, and then something special is going to happen. You get 1 plus root 3. What happens next? Minus root 3.
But those cancel.
And they cancel. And then minus 3. Because root 3 times root 3 is just 3, right? Awesome. And the reason that this works is because you chose these signs to be opposites, those middle terms are always going to cancel, right? That's going to happen every single time. So one way to check and see that you chose correctly is like, oh, did my terms cancel? Well, no, they didn't. I probably picked the wrong sign. So then your numerator is 6 plus 6 root 3 divided by negative 2. Awesome. And you've all heard of the distributive property for multiplication, right? There's also a distributive property for division. That's what that big fraction bar means. It means divide both pieces by negative 2. So divide the 6 by negative 2, which is? Negative 3. And then 6 root 3 divided by negative 2 is just minus 3 root 3. Does it make anybody nervous that this 2 doesn't affect that 3?
Well, it's being multiplied by the 6.
Yeah, so
Like if you multiply them, they're pretty much just 1.
I think about it as you kind of like used its power up. Like if you have 6 over 2, I don't know why I wrote 6. It's 2 times 3 over 2, and this 2 cancels that 2, and then it's gone, right? So that's the reason that it only doesn't affect the 3, it affects the 6, and it's used up. Its power is depleted. All right, so you'll see something in calculus more like this, but probably with like just x's in both expressions, not x's and y's. So what would the conjugate of the root x plus root y be?
Root x minus root y.
Root x minus root y. And whatever you multiply the bottom by, you multiply the top by, because it's only fair. And math is totally fair. Well, we try real hard. Okay, let's first do the numerator. So the first thing we're going to do is 2 root x times root x. So what does this 2 root x times root x make?
2x.
2x, lovely. And then 2 root x times minus y.
Minus 3x.
No, think they were multiplying. So the numbers multiply by numbers, right? Roots by roots. So the 2 times the negative 1 makes negative 2. And what stuff's under the root sign still? XY. Great. And it is important to be kind of systematic, like, first do the first variable, then do the second variable. Does that make sense? Okay. Then next we have, make that a little bit darker so you can see it. Next we have the 3y times the x, right? So that'll make minus 3 square root of xy. And the very, very last one. So first of all, what's the sign of the very, very last one? Plus. And then 3y, right? Okay. Over our denominator. So the denominator we have root x times root x is just x. And then we'll have minus root xy plus root xy minus y. And I think for now it'd be good to show your work and do the middle terms of that bottom fraction just to make sure that you know that they're canceling. Does that make sense? And what's your final answer?
X plus y. Well, that's the denominator.
Yeah, but you gotta be careful. You're almost right. X minus y. Details, man, details.
Oh, because the minus, I see.
The
Oh,
minus
oh,
carries,
yeah.
yep. So 2x minus 5 root xy plus 3y all over x minus y. And there's no more square roots inside the denominator, so you've rationalized. Okay. All right, so that's it for that lesson. And I don't know if anybody